Managing Director of the ISA 100 Wireless Compliance Institute. Welcome to our webinar today, A Sensible Migration Path to the Industrial Internet of Things. There is a question and answer tab that drops down from the arrow in your control panel in the top middle of your screen. So if you have questions, please type them into that tab, and we're reserving time at the end of the webinar to answer those questions. There are a large number of participants on the webinar, so we will leave everybody muted so that we don't have any static during the webinar, and we'll get to the questions at the end. So please type them in, and we'll get to it. So I'll go ahead and introduce the presenters today. The first presenter is Robert Asimony. He's the co-founder and CTO of Centero. So Robert has over 11 years of technical leadership in wireless. He's participated in a number of standards committees, including ISA 100. He's the co-chair of the IPSO Interoperability Group and publishes and presents widely in this area. Our other presenter is Raresh Ivan. He's also co-founder and VP of products for Centero with over 10 years of experience in design and management of embedded products. He's a hands-on software and firmware engineer. He served as editor for the gateway specification for ISA 100 WCI and has been instrumental in designing and developing radios and stacks and products for wireless products, including both wireless hard, ISA 100 wireless, and smart objects for IoT smart grid. So with that, I'll go ahead and turn the presentation over to our presenters, and we can start on the topics.
Thank you very much, Andre. This is Robert Asimony, and ladies and gentlemen, I would like to welcome you to this webinar. And I would also like to thank you for taking the time to join us in this exploration of the emerging industrial Internet of Things. As described in the synopsis of this webinar, we will focus on defining a winning strategy for the adoption of the Internet of Things technologies and architectural concepts in industrial wireless markets and applications. And, during the course of this webinar, we will delve into various novel technologies of which the emerging Internet of Things is comprised of, and we'll also discuss the applicability of these technologies to process and factory automation markets and related applications. And without any further ado, let's delve right into the definition of the Internet of Things. So what is the Internet of Things? This is a term that has received a lot of hype in the mass media, especially starting in 2012. And the picture shown in this slide attempts to capture the Internet of Things from the point of view of the application and market it accommodates. As you see, there are various market segments, and various market segments are depicted. And these are just a sample of the total market segments targeted. Given that the applicability of the IoT-based technologies is really not limited. Novel applications are being added each day to this wide gamut that is already being addressed by IoT technologies. And just recently, for example, I've heard of an Internet of Things-based application in which farmers are monitoring vitals for cattle. Now, think about it. If there's an asset out there, if there is a parameter that needs to be monitored or controlled, it can be easily accommodated by adopting Internet of Things-like technologies. Back 10 years ago, it was really called wireless sensor networking, and a lot of folks refer to it commonly as wireless mesh networks. That's not to say that the Internet of Things only utilizes wireless technologies. It is a combination of wired and wireless technologies. Now, this is the Wikipedia definition, and Wikipedia defines the Internet of Things as referring to a uniquely identifiable objects and their virtual representations in an Internet-like structure. I would like to provide you with my definition, which is not as sophisticated as the Wikipedia definition, and it's, in my opinion, the Internet of Things is simply an extension of the current Internet to physical objects that monitor and control various parameters in our surrounding environment. The term was originally coined by Kevin Ashton, an MIT technology pioneer that co-founded MIT's Auto ID Center and spearheaded the RFID-based technologies. So as I mentioned earlier, the Internet of Things is comprised of smart objects, and we call these smart objects in order to being able to differentiate them from traditional wireless sensing and control networking devices. Now, again, what is the industrial Internet of Things? I extrapolated the definition presented on the previous slide and we're defining the industrial Internet of Things as an extension of the current Internet to physical objects that monitor and control various parameters in industrial applications and market segments such as process and factory automation. And this is depicted in the figure below. One could also envision numerous other hybrid applications and markets between AMR and AMI, automatic meter reading and automatic metering infrastructure that would also allow for energy sub-metering and consumption optimization, energy consumption optimization in industrial plants. One could also envision controlling the lighting, monitoring and controlling lighting in industrial plants and industrial settings. What is a smart object? So a smart object is typically a constrained device. It's limited in hardware resources, in its processing capabilities, in the memory that it accommodates, both volatile and non-volatile. It's typically a device that senses or acts on its local environment, and it communicates with other objects or higher level systems. And some common examples are depicted on the right. Electric smart meters, smart lighting devices. To the bottom right, we show a water sump that's used in environmental monitoring. We also show some industrial instruments which are part of the IoT, temperature, pressure, vibration monitoring, valve positioners, and so on and so forth. But what makes an object smart? In our opinion, an object is smart when it embeds Internet-like connectivity. And this slide depicts the actual anatomy of the communication stack that is typically present in a smart object. As you can see, we are comparing the stack structure to the OSI reference stack, and everything from the network layer and up is based on valid IETF standards that have been widely deployed and vetted over the last 20 plus years. Now, in terms of the physical layer and physical and MAC layer underlying these smart objects, this could be there are many choices, anything from wireless technologies, 802.15.4, Wi-Fi, cellular, Bluetooth low energy, and the emerging 802.15.4G E5 MAC combination, which is widely used in smart utility networks, to wired technologies such as Ethernet or power line carriers. Again, I would like to highlight the fact that a smart object is really application agnostic. So everything that resides from the network, the layers that from the network layer and up, are typically application agnostic and are utilizing widely deployed Internet-like networking technologies. The physical layers are typically application specific, depending on the range and other requirements associated with the application or product. Customers or vendors typically choose the appropriate physical and MAC layer. I would also like to, let me revert back to the previous slide. Me and one of my colleagues used to joke around a couple of years ago, and we were having a discussion at one point, and he asked, well, when do you think a smart object will be smart enough? And to that I retorted with, I really do believe that a smart object will be smart enough when it will be able to connect autonomously to the internet and sell its data on eBay. Now think about it. There's a lot that implies a lot of things. It implies internet-like connectivity. The object has to be able to autonomously connect to the internet. So it has to use IPv6 routing or 6-loop and IPv6 connectivity. It has to use some kind of AES PKI-based security scheme and authentication scheme. At the transport layer, it would have to use UDP and TCP, and it will also have to accommodate some sort of web services in order to sell its data on eBay. Moving right along, a smart object network is a network comprised of wired or wireless smart objects, and it is an extension of the internet. It may include a gateway component to access other networks, but ideally it would incorporate no translating bridges for connectivity from the network layer and up. Now, communication, as networking, as mentioned in the previous slide, would be based on vetted IETF standards like IP, UDP, etc. And I would also like to highlight the fact that smart object networks can be insulated intranets or subnets. This is common in the current internet topology. Actually, the entire internet is composed of typically of isolated intranets, corporate intranets, or government intranets, or personal intranets that are separated from the rest of the internet through some kind of gateway. So just because a smart object is part of the Internet of Things, that does not imply that it's accessible or addressable by anyone out there. One will have to be granted access to be able to access these smart objects, which are part of these smart object networks or subnets. So this is really one of the main points that we would like to highlight during this webinar. The fact that ISA 100 Wireless was designed by the ISA Wireless Committee to be an integral part of the emerging Internet or industrial Internet of Things. And moving right along, I'm going to hand over the mic to my colleague Varesh, who will take you to a short ISA 100 primer, and he will also substantiate this claim that we made in the previous slide, where we believe that ISA Wireless is designed and architected to be part of the Internet of Things. All right.
Okay, thank you. Thank you for the introduction. And since you're controlling the slides, I'm relying on you to move to next slides whenever I make a longer pause. Thank you. So as you can see from this slide and the previous slide, we put on the ISA logo. And I would like to just make a very short introduction about the ISA. ISA is a founding sponsor of the Automation Federation, and it was founded in 1945 as a leading global nonprofit organization that is basically setting the standard for automation. There are tens of thousands of members worldwide, and ISA is focused on helping those members and other professionals solve difficult problems, technical problems. And WCI is the Wireless Compliance Institute. It provides real-world feedback for deployment of ISA 100 wireless devices and systems, and is fostering rapid refinement to the standards. WCI is providing market awareness, educational information, technical support, compliance testing, and so on for the ISA 100 family of standards. And we did have in this presentation in the beginning, the opening was done by Andre Ristano, which is heading the WCI, the Wireless Compliance Institute. But for more information about WCI, you can check their website at isa100wci.org. Now, in the following slides, we are going to cover an overview of ISA 100 Wireless, the standard, and its benefits. So ISA100 wireless, also known as ISA100.11a, is an open standard technology developed by ISA. It was ratified and it became a global standard. It's aligned to the SCN 300.328 directive for coexistence with other wireless technologies. And very important, is an open standard for anyone to implement and deploy. It's easily available via the internet and from ISA and WCI websites. There are no restrictions on using it. It's easy to use and deploy for end users, and it's written in a clear and concise manner. And it addresses the needs of users ranging from unsophisticated to networking experts. Next slide. ISA100 wireless was designed by experts in ISA organization, known for delivering industrial standards for over 60 years. A key point on this slide is that ISA100 was designed and was an end-user driven effort. And what you see on the slide are the end user's main architectural requirements defining the standard. So there are 11 major requirements listed here, starting with security, reliability, good power management. It needs to be an open standard. It needs to support multi-speed monitoring and multifunctional. It must be scalable, global usability. It does provide quality of service. Actually, it's a pretty sophisticated quality of service. It supports multi-protocols and is ready for control. Throughout those, based on those requirements, there were many breakthroughs while developing the standards. We have to mention the state-of-the-art security, which is all standards-based. The ISA100 wireless supports mesh network and dualcast. It does very good battery management for routing and non-routing devices. It's interoperable and tested for conformance by WCI. And it's all IPv6 based. Next slide. All right, so we did use a red color on this slide, but red is used, we mean by red just to attract your attention. This is a very important slide, especially for folks coming from an industrial world. ISA100 wireless standard defines all specifications, including security and management for wireless devices, serving applications from classes 1 through 5 for fixed, portable, and moving devices. It addresses performance needs for periodic monitoring and process control, where latencies in the order of tens and hundreds of milliseconds can be tolerated with optional behavior for shorter latencies. ISA100 wireless addresses most of industrial PAN field network applications and is covering safety, control, as well as monitoring type of applications. What you see on this slide is a shy attempt to highlight the building blocks of ISA100 wireless. I try to use different colors and group items as they relate to each other. So let's just go over them a little bit. Looking at the bottom line, the time diversity, frequency diversity, and acknowledge and the repeat request, those are a couple of features that are fundamental to ISA100 wireless, and they provide lots of benefits in terms of reliable connectivity and redundancy. And I will cover a little bit in the next slides those items. The red blocks represent building blocks specific to the spectrum management and coexistence. ISA100 wireless standard was designed with coexistence in mind, bringing peace to the mind of mind to the end user. We know that customers have other wireless solutions installed today, and have the need for any future system to coexist with those installed systems. So the standard features technology to ensure the best performance possible in the presence of other wireless networks. There are built-in mechanisms for spectrum monitoring and device management to ensure performance and scalability, while coexisting with the many other wireless devices deployed in field, and without being affected by the constant communication noise of a shared spectrum. There are features built into the IC100 wireless, such as channel blacklisting, automatically avoid congested channels, frequency and channel hopping. It has a mechanism to minimize the strain on any one channel by spreading signal over entire available band. Current implementation and specification is using DSSS, direct sequence spread spectrum. There are built-in hooks for dynamic power control and to limit the interferences. And IC100 is built for a very low duty cycle operation. It's somewhere in the order of 0.001 to 0.05% duty cycle. Short-time synchronous communication is using congestion in the network, and a very common feature is the clear channel assessment, listen before talk. The orange blocks cover topology, roles, broadcast, and routing. IC100 wireless has, in my opinion, a superior meshing scheme. Unlike other wireless standards for industrial and commercial use, IC100 supports multiple types of network topologies. The mesh network topology that you might be familiar with is supported, fully supported. But IC100 also supports star topology, which is just nodes without a routing role talking directly to a gateway. And then there are hybrid network topologies that combine the star and mesh topology to optimize routing and power consumption for constrained devices. IC100 also defines the concept of roles. There are no predefined device types. There are only logical roles. So a device that conforms to the IC100 standard must implement at least one of these logical roles. However, devices typically incorporate multiple roles. Those roles define actually the functional behavior of a device present in IC100 network. And a role is a collection of functions and capabilities. The graph routing, the routing in general, what's worth mentioning here, there is an entire chapter dedicated to the routing. However, because we don't have enough time to delve into great detail regarding routing, what's worth mentioning is that IC100 routing uses native IPv6 and 6LoWPAN in the mesh routing. It also has support for dual-cast, which enhances the reliability and redundancy in the network. And IC100 wireless also employs time diversity and determinism. Those systems that use the IC100 standard are fully deterministic, meaning that the central entity, the system manager, computes and allocates all communication resources in the network. The blue block, the security, is based on IS-128, which is a symmetric security scheme, and also the standard also specifies a PKI-based security using asymmetric mechanisms with public and private keys. There are FIPS 97 certified implementations of the security mechanism, as well as FIPS 140 certified products. This is a major achievement for this standard. I think it's the only standard out there for industrial wireless communication that was implemented and certified on platforms for NIST approved FIPS 140. I believe FIPS 140-2 at this point. The yellow block, multi-protocol in object model. This is a very interesting topic. The object model, for those of you familiar with the object-oriented programming concept, ISA100 Wireless is just like that. It was designed as an object model framework to be platform neutral, implementation and protocol independent. It is modular, reusable, and is capable of object encapsulation. ISA100 Wireless Objects describes state, behavior, and alarm condition for real-time process and application. Now, in this slide, as Robert mentioned before, ISA100 is aligned with the OC layers. And it can easily be used over many physical layers such as low power, Wi-Fi, Ethernet, cellular, and PLC. Current specifications and implementations are based on the popular and field-proven IEEE's 802.15.4 PHY, which is operating in the 2.4 GHz ISM band. The IEEE supports many working groups to develop and maintain wireless and wired communication standards, and the 15.4 standard is just one of the many out there. And 15.4 defines the PHY and the MAC layer of the open systems interconnection, or the OC model of the network. And more exactly, the PHY defines frequency, power modulation, and other wireless conditions of the link. And the MAC defines the format and the data handling. The 15.4 category is probably the largest of the standard and has many categories. One such subcategory is the 15.4G, which is a PHY amendment to the 15.4 to provide a standard that facilitates very large-scale process control applications, which are capable of supporting large geographically diverse networks with a minimal infrastructure, potentially millions of fixed endpoints. The 15.4G standard was published in April 2012 as a radio standard. And the key point here is that ISA100 Wireless could easily be ported to alternate PHYs such as the 802.15.4G. What I want to mention is that the 15.4G, also known as the Smart Utility Networks, or SUN, facilitates those large and very large scale process control applications. And it's applicable not only in the industrial network, but also in the smart grid networks. And it addresses outdoor low data rates and smart metering utility networks as well. I would like to summarize on this slide that ISA100 Wireless could easily accommodate alternate PHYs as the 15.4G. And talking about other layers, following the OC model, let's move on to the routing and the TSCH layer. The 15.4E, just a quick note, the IEEE 15.4E layer specification, time synchronized channel hopping, is basically a subset of ISA100 Wireless MAC. Basically, is the ISA100 Wireless MAC without the routing. ISA100 Wireless routing is of type mesh under, being part of its MAC. However, because it's a layered architecture and it has built-in service access points, SAAPs, replacing its current routing by routing algorithms or specifications such as Ripple or RPL-based layers is perfectly possible. For those of you that don't know, RPL is short for IPv6 routing protocol for low power and lossy networks, and is a routing protocol defined by IETF. I believe it's RFC 6550 and was published in March 2012. And Ripple is using key concepts such as DODEG. Don't ask me what that means. Actually, it's direction-oriented directed acyclic graph and objective functions to route messages in the network. So the key point here is that ISA100 can easily use IEEE's 802.15.4E, TSCH, and Ripple for routing. Now, talking about TSCH, if you could go back to that slide for a second, TSCH means time-synchronized channel hopping. And it's a basic building block of the MAC layer and is composed of time slots and channels. Time slots are fractions of time, usually 10 milliseconds long, but configurable. They are organized in frames and subframes. Okay, next slide. Going back to the idea of those slides, that IC100 wireless is aligned to the IoT. As mentioned before, IC100 wireless is architected in the spirit of the OSI layers. It's one of a kind, stands out there. It does not compare with wireless HART or Zigbee or other similar standards, just because IC100 wireless is the only one that follows the OSI layers. All IC100 wireless devices are IPv6 enabled, and the IP connectivity is realized to compress IPv6 and UDP messages. It is using EY64-based addressing scheme. All field devices have IPv6 addresses for global addressability, as well as 16-bit 15.4 short addresses. Now, in terms of IPv6 connectivity, as I mentioned before, the network layer of the IC100 wireless is based on IPv6 and is based on 6LoWPAN. And 6LoWPAN is a compression of IPv6 for constrained mapped objects. It provides a huge addressing space of quadrillions of devices, and you can use, because it's an IP standard, you can use existing networking tools and infrastructures to manage IC100 wireless networks. Of course, it supports all the other benefits of IPv6, like stateless address photo configuration, plug and play, and so on. The IC100 wireless alignment to IoT is more visible when you compare the stack architecture side by side with the OSI model. The stack is structured in physical layer, which is 802.15.4, TACH plus routing, which is a data link. Then on the network layer, you have an IPv6 6LoWPAN based architecture. On top of each, the devices communicate using UDP messages secured by AES and PKI security. This is the kind of security that your bank uses when you log in to check your account balance. With the session layer, we have contracts in IC100, and then objects at the presentation layer, on top of which you can run your own application. So the entire IC100 stack is constructed employing widely used, industry accepted and proven standards. And it was architected in strict adherence to the reference OSI model. Now, I will pass the mic back to my colleague Robert, and Robert will trace an evolutionary path to IC100 wireless for an even closer alignment to the emerging IoT. Thanks, Robert.
Thank you, Raresh. So over the course of the last slides, Raresh tried to substantiate our claim that IC100 wireless is perfectly aligned with the emerging industrial Internet of Things. Now, this slide just recaptures some of the points that were made in the previous slide. So due to the committee's architectural and standards alignment decisions, IC100 was consciously architected to be part of the emerging Internet of Things. And both Raresh and myself were part of that standardization effort. We were there when these decisions have been made, such as inclusion of IPv6 and 6LoWPAN connectivity, and aligning utilizing UDP datagrams at the transport layer, and so on and so forth. Now, let's talk a bit about the backbone infrastructure. The backbone infrastructure defined by the IC100 wireless standard is compliant to the Internet of Things. Actually, the standard mandates that the entire backbone infrastructure utilizes IPv6 addressing and routing. It does not specify any particular PHYs, hence one can envision a backbone infrastructure that utilizes multiple different wired or wireless technologies that all utilize IPv6 connectivity and IPv6 addressing and routing, as well as internet-like security, such as TLS or DTLS. Now, I would like to propose an evolutionary path to where we would adopt 802.15.4G on the backbone infrastructure. Now, why would that be of tremendous advantage to the ISA100 wireless infrastructure and to its positioning within the emerging industrial Internet of Things? By adopting IoT-like technologies, this allows us to deploy very low-cost backbone routers. The backbone infrastructure could be arranged in a multi-hop, long-range, path-redundant topology. So envision a backbone infrastructure that is utilizing a multi-hop, long-range technology such as wireless technology such as 802.15.4G, and it would allow for the formation of different subnets centered around these backbone routers. Now, each one of these backbone routers would, of course, support the ISA100 mandated 15.4 wireless PHY, which operates in 2.4 gigahertz. So your typical instruments, your pressure transmitters, your instruments that will be engaged in process control and automation will still operate in 2.4 gigahertz, but a backbone that will be based on 4G will also allow and accommodate devices engaged in energy submetering, energy consumption optimization, or industrial lighting, controlling and monitoring the lighting present in these factories and plants. So one can see the advantages are obvious, right? A single infrastructure that's arranged in a multi-hop topology based on 15.4G that supports both process instruments engaged in process automation and control, as well as smart energy monitoring and optimization, lighting, and so on and so forth. This slide captures the essence of what was presented during this webinar. So this table gives a snapshot of what is currently present on the backbone and in the field network. So both the backbone and field network, ISA100 wireless backbone and field network, are based on IPv6. All the devices are addressable utilizing IPv6 addresses. They also support IPv6 routing. The backbone, the standard mandates that the backbone routers support IPv6 routing. And as far as the field network is concerned, IPv6-based routing is permitted. IPv6 discovery is permitted on the backbone. On the field network side, ISA100 defines its own network discovery mechanisms. In terms of security, the backbone would be based on TLS and would also support certificate-based authentication. The field network currently supports AES symmetric encryption scheme at the transport layer, as well as PKI certificate-based authentication. And going down again to the communication media, any physical layer is allowed on the backbone as long as it supports IPv6 addressability and connectivity. So one could foresee how the entire ISA100 construct could run on different physical and MAC layers. And again, in conclusion, I would like to reiterate the main point that we were trying to substantiate throughout this webinar, namely that the ISA100 wireless extends the Internet of Things to the industrial Internet of Things. And it really extends internet connectivity to wireless devices, wired and wireless devices, which are engaged in various market segments and applications that are part of the emerging industrial Internet of Things. Now, as an added bonus, given that you all were so patient listening to us for 45 minutes, we also included a very deep technical comparison between the 802.15.4 2.4 gigahertz physical layer, which is currently utilized in ISA wireless, and a comparison to the 802.15.4G specifications and performance parameters, which are part of the Smart Utility Network standard, which is ratified by the IEEE in 2012. I'm not going to dwell too much on this slide. This is included as an appendix for those of you who would like to get even more in-depth technical specs and information in regards to 802.15.4G. So this presentation and webinar will be posted on the WCI website, and we strongly encourage you to download it and revisit it as needed. Now, as far as if you need any additional information, we are here. Feel free to contact us anytime. Contact us directly, Raresh or myself, or you could also contact Andre Ristaino. All the contact information is provided on this last slide. And I would like to thank you for taking the time to listen to us and for joining us in this exploration of the emerging industrial Internet of Things. And with that being said, I'm going to open the floor for the QA session. So Andre, back to you.
Thank you for the presentation. So there's a couple questions. One was one of the listeners was asking, what is the IETF?
Right, the IETF is the standards body that is in charge of really running the internet. It's composed of, I think, over 10,000 engineers that are working on have been working arduously over the last 20+ years in defining the standards that run the internet, such as IP, UDP, TCP. So the entire internet is governed by these standards, and it's operating utilizing networking standards defined by the IETF. It's a standards organization.
Thank you. So another question was, with Internet of Everything, or Internet of Things, does that mean that every IP addressable device is visible and accessible to anyone on the Internet around the globe?
No, that is not implied. So as I think I touched on that on the 5th or 6th slide. So just as the existing Internet, in the existing Internet infrastructure, not every machine is accessible or accessible by anyone out there, right? Most corporate networks are really isolated intranets that only allow access to authorized or authenticated users. So smart objects that will be deployed as part of these IoT networks or subnets are not necessarily accessible by anyone out there. Being a smart object implies that the actual device supports Internet-like technologies and connectivity, but it does not necessarily imply that anyone out there will be able to access it. I mean, that's why we have these fairly complex security and authentication schemes in order to prevent that from happening. Just like on the current internet, you can access somebody else's bank account, right? Or you can access a machine that you're not authenticated or authorized to access. So the same paradigm stands in the industrial Internet of Things, or in the Internet of Things as well.
Okay, thanks. I'm just waiting on any other questions. We'll give it another minute or so. We don't see any right now. If none others are sent in, we'll sign off, but we'll give it about another minute. And so if anyone has questions, please just type them into the Q&A screen. Yeah, so Robert, there was a question to clarify. Is ISA 100 wireless using 802.15.4 or 802.15.4G? today?
Today, ISA 100 is based on 802.15.4, which was ratified back in 2006 by the IEEE. And what we are proposing is that we start also utilizing 802.15.4G primarily on the backbone infrastructure. ISA 100 was architected and designed to be ported to various different physical layers and MAC schemes without any modifications. So one could foresee the entire ISA construct or communication stack being ported to several different physical layers. And that's very much in tune with the whole concept of the Internet of Things. As mentioned during the webinar, the Internet of Things or smart objects do not imply any particular physical layer connectivity or any particular communication media, right? Just as the current Internet, which runs from anything from mobile devices to tiny little embedded devices to large servers, utilizing Ethernet, Wi-Fi, cellular, and so on and so forth. And the emerging Internet of Things and the emerging industrial Internet of Things will be based on several different physical layer or communication media, allowing, and the choice of the communication media is highly influenced by the application you're trying to accommodate. So one could foresee that devices engaged in process control and automation, such as pressure transmitters, temperature transmitter, valve positioners, corrosion monitors, and so on and so forth, will continue utilizing the 2.4 gigahertz physical layer. But as mentioned during the webinar, these networks could be augmented with ISA 100 wireless devices. They would utilize the 15.4G physical layer. Now, the 15.4G physical layer was architected by the IEEE and is an extension of the an amendment to the original 15.4 standard. And it targets smart utility networks. So it was designed and architected with smart grid, automatic meter reading, automatic metering infrastructure type applications and requirements in mind. So that is one of the things that we were proposing, is that we augment the existing ISA 100 infrastructure, which utilizes the 2.4 gigahertz 802.15 physical layer, with devices engaged in energy sub-metering, basically monitoring the consumption of various machinery in the plant, optimizing the energy consumption of various machinery that operates in the plant, controlling the lighting inside these plants and factories, monitoring their state, controlling them. These are just a few of the applications that could be accommodated by the 15.4G physical layer.
Yeah, so a couple of people have asked if this presentation is available to download. The answer is yeah. On the ISA 100 WCI website, there's a tab called Learning Center, and this webinar and the slides will be posted up to that within the next 24 hours. So yeah, you can download the webinar and the slide deck.
Andre, any other questions? I see.
Yeah. So how would you envision the 802.15.4G aiding mobile applications?
Could you repeat the question, Andre? How will I envision 15.4G?
Yeah. How would it benefit mobile applications?
Oh, mobile applications, I see. 15.4G is not really designed and architected for mobility. Now, it does offer extended range when compared to the 15.4 2.0 physical layer that operates in the 2.4 gigahertz spectrum. So I think it's, in terms of accommodating mobility, it would be capable of accommodating limited mobility, mobility within the actual confines of the deployed network. So I would say that 15.4G is very well suited to accommodate limited mobility within the confines of the plant. Of course, it wouldn't be able to accommodate mobility of the likes of a cellular connection, right, where you have infrastructure deployed, largely deployed over very large geographical areas. But it sure can accommodate mobility within the confines of the industrial plant, given the extended range. Any other questions?
So, yeah, there were a couple questions about the ISA 100 wireless and plans to incorporate the new radio technologies into the PHY layer. And so I'll just quickly answer that. So the standard was designed to be able to have new PHY layers inserted in and without disrupting the rest of the technology and applications. So those decisions would be vetted through the ISA 100 Standards Committee at ISA. And so consideration for implementing the new PHY or having two versions with two different PHYs and all those technical and market considerations would be done in the ISA 100 Standards Committee. So they have a research and evaluation subgroup or working group that evaluates new proposals. So that's kind of a broad brush for that, but I think that's the best answer for today. Okay, so that's pretty much it for the questions. Raresh and Robert, thank you for your time and the presentation. Again, this webinar will be posted up to the website and available within 24 hours. Hopefully we'll have it posted up today. So thank you again, and we're going to go ahead and we'll end the presentation.
Thank you so much, everyone. Thank you for taking the time to attend. And look forward to your questions.